Welcome back to discussion 31, where last time we did discussion 32 and now we're going to 31 by the formatting on the sheet. So this is fluids. We're talking about fluids today. So we're talking about Crater Lake in Oregon being the deepest lake in the United States with a depth of 655 meters. The density of fresh water is 1 times 10 to the 3 kilograms per meter cubed. So if the air pressure above the lake here's our P naught, it's given as 8 times 10 to the 4. We'll just write it, may as well be consistent. Pascals. What is the absolute pressure at the bottom of the lake? Well, we have this pressure as a function of depth, right? We could call it H. Well, at this point I called it H is your depth. That's what I'm saying, okay? Pressure as a function of depth. Well, we have rho, density of the medium, times G times the depth plus the initial pressure. So this is simply a little bit of arithmetic. And then we just plug this in and we get 1E3 kilograms meters cubed times 9.81 meters second squared. 655 meters plus 8 pascals. 8e to the 4 pascals. Okay, and before I plug it into the calculator, we can just look at units to see how this is going to work out. Well, we have meters squared over meters cubed. So we have kilograms per second squared per meter. So the units here are going to work out as this. So Pascal, so that all makes sense. So now we're in units of pressure. So we plug all that in anyhow. So absolute depth is equal to 6.51 times 10 to the 6 pascals. Which seems super high, I mean, but we're at the bottom of a really deep lake, you know. We're like 650-ish meters down, which is, I don't know, 1,800 feet, almost 2,000 feet. So yeah, that works out. That makes sense to me. So part B. What is the force of the lake's water on each window of a submarine near the lake bottom if each of its circular windows has an area of 100 centimeters cubed? Okay, squared. Excuse me, 100 centimeters squared. So let me just be more clear. This is what we're given, right? And that means that we're here, which means that we're here, which means that we are here. Okay, so this is the area of a window on a submarine, and we want to know what the force on that window is. And that's important to know because if you're going to build a submarine, you don't want the windows to break and water to come crashing in, right? So you need to have it withstand whatever pressure, whatever force is at the bottom. Okay. So our standard relationship is force over area is equal to pressure. Well, we know what the pressure at the bottom of the lake is. This is what we want to use. Right? This is the pressure, the absolute pressure at the bottom of the lake. So the absolute pressure at the bottom of the lake times the area, okay, that's what we want, times 10 to the 6 pascals. Now we are at newtons. Okay, let's double check our units. Pascal is a kilogram per meter per second squared. Then we multiply by meters squared. That gives you kilograms meters per second squared, and that is a newton, so that's good. Okay, next problem. Okay, we have another submarine. This time it's got a bunch of cameras on it. It's 2 meters in radius. And it finds a shipwreck. So here is our submarine. It's got a bunch of cameras on it, right? And then it goes down into this, what is it, lake bottom? Oh, it's the Atlantic Ocean. Right, that makes sense because we have a shipwreck. Okay. So the depth is this. Depth is 1.75 times 10 to the 3 meters. Seawater density, 1.03 times 10 to the 3 kilograms per meters cubed. And air pressure, we know two things. We want to know the absolute pressure at the depth of the shipwreck, and we want to know the buoyant force on the submersible camera thing at the depth of the shipwreck as well. So part A, we pretty much just use the same formula that we did before. This is going to be the medium times the depth plus the initial pressure, right? And this here is going to be the initial pressure. So this is like at the surface, sea level we call it, right? So let's move this. We don't need that yet. So we just plug in. Plus 1.013 e to the 5, right? We've already checked the units on this equation, so I'm certain that they're going to work out, and this gives you a value of 1.78 times 10 to the 7 pascals, which is a lot. But again, like what was the last one in this lake? 10 to the 6 pascals, and now we are at 10 to the 7 pascals. So yeah, I mean, we're super deep under the water, right? So that's fine, that makes sense. So that is the absolute pressure. Okay, and then it wants the buoyant force. So now we need to consider, we can pull up this diagram here. So under the water, we have two forces acting on this submersible, right? We have the weight force pulling it down towards the bottom, and we have a buoyant force pushing up. So the buoyant force is the weight of the water that is displaced by the object itself. So let's say this thing is just kind of sitting, it's not moving up or down, right? So we're in equilibrium, as submarines tend to do, right? So now we have a buoyant force pushing up minus a weight force. So at this point, then we have a buoyant force is equal to the weight force. So we break our buoyant force down into rho, because if it's equal to mg, right? So we're saying our buoyant force is equal to the weight force, which is mg. So that means that our mass is going to be density times volume times gravity, right? So that's really what we're looking for. This is the volume of the water that is displaced, which we can use the volume of the object itself, right? And this would be the density of the medium. So the buoyant force is going to be the density of the water times the volume of the sphere, right? This thing's a sphere with a 2-meter radius. So that's going to be 4/3 pi, and then it's r cubed, right? R cubed is going to be 2 cubed is 8. Okay, and then times g, and then so what was our density? 1.03 times 10, what was it, 10 to the 3? Yep, kilograms cubic meter times 32 pi over 3. This will be meters cubed. So we see the meters are going to cancel right away. And then times 9.81 meters per second squared, which gives us units of newtons, which is what we want. And so when we plug this in, we end up with 3.23 times 10 to the 5 newtons. There we go. Which is high, but again, we're, you know, nearly somewhere really far down in underwater, right? So that makes sense. We're going to have high pressures and we're going to have a lot of force. Okay. Looks like I wrote this down wrong. I ended up with 3.38 times 10 to the 5 newtons. So I was just copying down. A little sloppy, I guess. Okay, so the next problem, we're given a rectangular block of styrofoam, and we are told that the length is 25 centimeters, so 0.25 meters. The width is 0.15 meters, and the height 0.12. Okay, those are the dimensions we're given. And then we're told that the styrofoam density is 3 times 10 to the 2 kilograms per meters cubed. We want to know what is the volume of the block that is submerged first, right? And then secondly, part B is a copper block is placed on top of the styrofoam block so that the styrofoam block is, so the top of the styrofoam block is all the way just level with the surface of the water, and then we can find out what is the mass of the copper block. Okay. Okay, so here's the block. Here are our dimensions and the density, right? So we can use the same condition that we had before. So that we put the block in the water and it's floating, right? We have a buoyant force pushing up on the block, and we also have a weight force pulling down on the block. So there is a weight force, and there is a buoyant force pushing back up. Right, this thing is in equilibrium, and so again we have the same condition that we had before. So now we have, for buoyant force, we have density of the medium, which is the water, times gravity, times the volume of the water displaced. So I'll just put this volume of the water displaced. And that's actually what we want to find out. We want to find out how much water is actually displaced. That's what we're asked to find. So, and then on the other part we have density of I don't want to call it, like, what is it? The styrofoam, right? Density of the styrofoam times gravity times the volume of the styrofoam block. Okay? All right, so we need a few things, right? So if you calculate volume of the styrofoam block, you get 0.0045 meters cubed. We know density of water, 1 times 10 to the 3 kilograms per cubic meter. Well, actually, I looked it up, and I ended up with 997 times 10 to the 3. No, that's not right. 997 kilograms per cubic meter. Okay. So I think we have everything we need, right? So these are going to cancel. And then we just want to know what volume is displaced, right? What does it say? What volume of the block is submerged? And well, that's going to be equal to the volume of water that is displaced by the amount of block that is submerged, right? So as this thing goes under the water, it's just going to move a volume of water out of the way for as much as it's submerged. Okay, so that means that we have rho of the styrofoam, density of the styrofoam over density of the water times the volume of the styrofoam block, and that's going to equal 3e to the 2 kilograms. Let's write it out. Per cubic meter, and then 997 kilograms per cubic meter times, what was it, times 0.0045 meters cubed. So these units cancel, and we're left with units of volume, which is good. So after plugging that in, we get the volume of water displaced is 0.00135. That's a good place to stop. So what does that give us? Around right, 1.35 times 10 to the negative 3 cubic meters. That's really small. That's almost nothing. I guess that's what we would expect from a styrofoam block. I just expected there to be some of the block to be submerged, but it seems like almost none of it is submerged at all. So that's pretty interesting, actually. And just recalling how we found it, remember we set our equilibrium condition with our balance of forces, right? And then we had buoyant force is equal to the weight force, where weight force is mg, but we don't know mass, so we need to use the density times the volume times g. And the same thing for the buoyant force, we have density times the volume of the water displaced times g. So that's how we did that. Next problem, wait, we still have some of this problem to finish. So we need to figure out what is the mass of the block. Okay, so we're given pretty much the same scenario, except we increase the mass that's on top. We're told how much is submerged. We know that it's just the volume of the styrofoam block that's submerged. So now we know that the water displaced, the volume of the water displaced is just going to be the volume of the block itself. Right? Because we're told that this thing has gone underwater. We've placed let's see what's copper. Let's go with this one. We've placed a copper block on top of it, and that has caused us to submerge just so that the top of the block is in the surface. Okay, so now we want to use the same condition. So we have weight force mg is equal to, because we're not moving, right, is equal to the buoyant force, which is density of the water times g times the volume of the water displaced. Okay, well, so the g's are going to cancel. Mass is going to be, what do we have? We have mass of the copper plus mass of the styrofoam block, which we don't know, but we do know its density and its volume. So this is the styrofoam block and the volume of the styrofoam block, right? So we can do that. So this is the mass of the block. This is the mass of the copper, right? Sorry, styrofoam, copper. Okay, so now we just plug that in. Mass of the copper block plus this times this, excuse me, and then we have these values. Okay, so notice now, if I solve for this, I have density of the water times volume of the water displaced minus density of the styrofoam times volume of the styrofoam block, right? Well, the density of the water displaced is the volume of the water displaced is the volume of the styrofoam block. So those are equal. So now what we have is volume of the block. We'll just say styrofoam block, right? Times the difference between the densities. That's what the mass of the copper is going to be. So we have 0.0045 meters cubed times this value minus, what was our value here? Density of the styrofoam block is what? 3e to the 2. All right, this was 997. That's right. Let's stay consistent. Minus 300 kilograms meters per meter cube, right? Per cubic meter. So these units actually cancel, and we're left with kilograms, which is what we want. So that's kind of nice. We plug this in, and I ended up with 3.14 kilograms per cubic meter. Nope, sorry, those go away, right? Kilograms, 3.14 kilograms. So that's your answer. Next problem, number 42. Okay, so we are given a setup where we have this weird piston thing, and so it's like what it says, example 15.4. Example 15.4. So check that out, because that's pretty much what we're given. And there's this tube with it's bent like a U kind of, and on each end there's a small piston, and on one of the pistons you have a car. Okay. The larger piston, you have a car. We're given two cross-sectional areas, right? 0.25 square meters and 1 square meter. So on the larger piston, there's a car with weight mass 1.2 e to the 3 kilograms. Anyway, here's the diagram that I drew, which I think it looks pretty nice. There's a guy sitting in the car. I'm including him in the mass. We don't need to add extra mass. So here's your piston, right? That's the big one. Here's the car. Here's the little piston. Okay, so there's like some fluid in here. There's some fluid inside. So we'll kind of do this. And this thing kind of comes up, right? So we want to know, in order for this thing not to move, what is the minimum force to be able to support this on the larger piston? That's what we're looking for. And so what we need to use is something called Pascal's principle. And pretty much what that says is, in a situation like this, where the fluid is uniform, any change in pressure in the system is going to be equal to changes in pressure in the system, right? So it would be like, if there's a change in pressure over here, it's equal to a change in pressure over here. So change in pressure is equal to a change in pressure. And what that means is that we have now a force over an area is equal to a force over an area. We'll call this 1 and this 2. So now we want to find, so let's see, which one was the larger? A2 was the larger, that's what I assigned. So this one is the largest one. So we want to find then what is the minimum force where we can support this car. Okay, so F2 is going to be the weight of the car. This is the force exerted by the car on the piston. Okay, so what is that? That's going to be 1.2 times 10 to the 3 kilograms times 9.81 meters per second squared. Right. And then we have A1. So we're going to do this. We're going to say F1 min is equal to 0.25 meters squared over 1 meter squared times all of this. And then we just plug that in. value of 2,943 newtons. And using scientific notation, we would write it as this. I suppose you could do that. If you wanted to keep 3 sig figs. So that's up to you. Either way, that's the answer. Pascal's principle. So the next problem is number 70. Okay, a vessel contains oil of density. You're given a density, and then it's resting on top of a mercury with a density. So our vessel, just some container. I don't know. I'm gonna picture it like a barrel. It could be a sphere. It doesn't really specify. It's not totally necessary. So we have something like this. Okay, let's do this. Make it easy. Anyway, so we're told that there's oil on top and then mercury in the bottom, right? So there's mercury down here, and then there's going to be some, I don't know, some kind of oil on top. Then we're told that there's a sphere, a solid homogeneous sphere, and then it's just kind of floating with half of its volume in one of the liquids and half in another of the liquids. So, okay. Here's our sphere. And then we're, right, floating, like, what is it, half here and then half down here. I'm just having fun. I guess I should get moving on the problem. Okay. What is the density of the sphere? Right. Actually, this is a pretty cool problem, and so I think that's why I'm taking time to do this, because, okay, so this thing, so we have oil up here, we have mercury down here. We're given densities for both of those, and then we're told that there's a sphere that's just sort of floating in the middle, right? So if this thing isn't moving, well, we have an equilibrium condition that we can use. And so we're going to have, from the oil, there's going to be a buoyant force pushing up. From the mercury, there's definitely a buoyant force pushing up. Even though this is less dense, it will still exist, right? And then the weight force is pushing down. So we only have really one weight force, mg, right? We have a buoyant force and another buoyant force. So here, let's set this up. So we have weight force plus buoyant force, we'll call this oil, plus buoyant force, we'll call this mercury, equals 0. The sum of the forces is 0. We have no action. Okay. So now what we do is we break this down into using Archimedes' principle, right? So we have, we'll call this density of the sphere. And that is what we're after. We're actually looking for this variable right here. So density of the sphere times gravity times volume of the sphere, plus we have density of the oil times gravity times volume displaced of the oil, right? Now we have the buoyant force of the mercury, so that's density of mercury times gravity times volume displaced of the mercury, all equal to 0. So now we can cancel some stuff out. By some stuff, I mean gravity. Okay, and then we have, what are we left with? Density of the sphere is equal to density of oil times volume of oil plus, density of the mercury times volume of the mercury displaced all over volume of the sphere. So now recall that we're told that the volume of oil displaced is half. So this thing is sitting with half of its volume in the oil. So this is half of the sphere's volume up here is displaced, right? So that means that we have density of the oil times volume of the sphere by 2. Then we have same thing for the mercury. This thing is sitting half in the mercury, so half of the volume of the sphere has been displaced in mercury. So volume of the sphere by 2, all over volume of the sphere. Now what does this leave us with? It leaves us with density of the oil plus density of the mercury times 1 over 2. This will give us our answer. And so when we plug that into our calculator, we end up with 7,200 kilograms per cubic meter, or 7.20 times 10 to the 3 kilograms per cubic meter. You could write it either way. And that's it. That's how you do that problem. Using Archimedes' principle, we can break everything apart into the relative volumes that are displaced and the densities. So that's pretty cool. All right, well, that's the last lecture of the semester, so thanks for a great semester. Hope everyone's doing well in their class, and if you have any questions, feel free to reach out. All right.